All right, so among a limitless number of applications of a definite integral, then we can apply a definite integral into finding the volume of a solid. Okay, and finding volume, applying a definite integral into finding volume is a very common application out there. And so in this particular video lecture over here, allow me to introduce the kind of problem where we apply our understanding of a definite integral into finding the volume that's generated by, so the volume of a solid that's generated by a rotated region. Okay, so here's the title over here. So we're going to learn how to apply definite integral into finding volume of a solid. Okay, volume of a solid generated by a revolving or rotating region. All right. And so we really have to take it step by step into the study, because the kind of problem we're doing will get from the simpler kind of problem and it become more and more advanced kind of problem like that. So I will definitely have to break this particular lecture into 2 or even more parts where I can introduce, the classes of problems where it goes from the simpler one to the harder one. Okay. But so here we go. This is mainly the entire lecture here, including all parts together. It's the volume of a solid. We learned how to apply definite integral into finding a volume of a solid that's generated by a revolving region, like that. Okay. And so now I'm going to need more board space, so I'm going to erase this away. And so let's start out with a very basic idea first. Let's start out with the most basic type of problem right there. And then from there, once your understanding become more mature, then we're going to push it we're going to extend the idea into a more complicated and advanced problem. Okay, so let's say we're starting out with having just a curve. Okay, and you can think of this curve as a function f of x. This curve can be expressed as a function f of x. Here's the x-axis, here's the y-axis. Okay, the curve here is and at this point, thinking of that as a function f of x or whatever is not even important yet. The point is we have a curve. And so, in that curve, well, in respect to the x-axis, it has a starting point and an ending point. So we have a start at A and we have an ending at B. Okay, and so for a simple start, let's start out with a basic picture like that. We simply just have a curve, okay? And with that curve right here, now I'm going to restrict that curve into an interval on the x-axis from x equals a to x equals b. And so now, from just the way how the picture is making it, we have an area. So right now we have an area, a region. So what I have here is a region that is and just right now, I don't really want any viewers or any of my students to worry too much about the function of the curve or whatsoever, or the expression, the representation of the curve. Just simply think about we have a curve, and then so from that curve, I'm restricting that. I'm going to restrict that curve on the x-axis here. We can restrict that from a starting point A to an ending point B. So allow me to repeat that part. And then between the curve and the x-axis itself, we can create an area. So just like in the picture here is describing, we have an area. Okay, so, or more generally, we call that as a region. Okay, and so now just right from that picture, right from this picture with the region that we're looking at right now, no need to worry about what function this is. Just simply think about we have a function, we have a curve, okay, and then there's that region between the x-axis, for now between the x-axis and the curve, and then and between a starting point on the x-axis, relatively on the x-axis, and an ending point relatively on the x-axis as well. So anywhere from A to B on the x-axis. There we have a region. And so now with that region, now think about, I'm going to take that region and rotating it. Okay, I'm rotating it. So if I'm rotating it, the picture is going to become as following. Well, if we now imagine that we're putting our eyes looking straight, so this is my eye right here, looking straight into the picture, and so of course, if we're looking straight into the picture, this x-axis now, because as I was saying earlier, we're rotating about the x-axis. Okay, we rotate this area about the x-axis. And so in that way, I highly recommend start triggering up your imagination. When we get into this problem, you have to start triggering up your imagination. Okay, so you imagine that you place your eyes looking right at the x-axis. So the x-axis is pointing right at your eyes right there. Okay, so you're looking straight through it, and then in the meanwhile, imagine that we're going to take the whole region here and rotating it. And so that's why this thin slice right here now become a circular cross section. Okay, and that same thing right here, this starting end of our region right here, when we're rotating it, that thin cut right there becomes a circular region, and so we're creating another duplicate of that exact curve on the bottom end, but just simply because as we're rotating that curve and forgive me that I'm not an artist, so I can't make the perfect picture, but see this area, once we're rotating it, we have a solid. Okay, and where now I'm trying to make my point here is that each part here, each slide here, once we're rotating it, each stripe right here, once we're rotating it, it's generating a cross section, a circular cross section for us. And think about, we put our eyes to be along with that, to look right at that x-axis, and the x-axis is the axis where we're rotating our picture about. Okay, we're rotating our region here about the x-axis. Okay, and so so now let me point out a couple of terminology right here. So yes, so that's the situation. We have an area and we're rotating that. So in this specific problem, in this specific picture I'm bringing up, then we're rotating about the x-axis. So this x-axis here is referred to as the rotation axis. Okay, the axis that we take the whole picture and rotating it about. All right, so allow me to pause this picture here. Let me navigate to the other board. I'm going to move over to the other board, and I'm going to create a different graph. And so now my point is, the x-axis is not the only rotation axis that can exist out there, that we can work out there. So again, on the x and y system, we can also have a curve. We can also have a curve. So that's why, back to what I was saying earlier, now I can hopefully clarify a little bit. I don't need anyone viewing this video at this point to worry about, is this a function in terms of x or is this a function in terms of y? We don't need to worry about that yet. So really get that part highlighted for me. I don't need anyone to see this curve as a function of x or this curve as a function of y. That's not the point yet. Okay, but now here, similar with that idea I have expressed on the other board. This curve right here, in between this curve and the y-axis this time, there will be a certain area trapped between. Okay, and then I'm gonna restrict that area on the y-axis, relatively to the y-axis, in between a certain interval from, how about from C to D right here. Okay, but C and D, these are the start and end on the y-axis. Okay, and so in the way how my picture is setting up right there, and I just now realized I made my area a little too large, so eventually it could give a challenge for me to draw the later picture. So how about I'm going to make it a little smaller. Okay, so my D point is right here. That's D. But now once again with a region, the region is formed by a curve and one of the chosen axis. So instead of the x-axis, like in the previous picture here, we chose the y-axis. So the curve and the axis, and between two values being the start, namely the start and the end right here. And then I'm going to take that region, and this time I'm going to revolve. I'm going to rotate this whole region. And so in formal terms, we're revolving it. Okay, we're taking this whole region. Treat the y-axis here. So now the plan here is I'm going to rotate this region about the y-axis. So we can do that too. So I'm saying we can do that. That means, there will be problems where we are asked to find a volume that's generated by, it started out by having a region, and then we take that region and rotating it about the y-axis. That's how the solid is generated. So now let's imagine again, and you need to start pushing out your imagination. You need to start triggering up your imagination. So now when I'm rotating it, this time I'm going to place my eyes, think about it, I'm going to, similar to the picture I've had on the other board, this time I'm going to place my eyes looking right down. This is my eye, I'm looking straight down. So the y-axis pointing up, but now I'm looking down on it. Okay, I'm looking down on it, so the y-axis come right at me, and the picture is rotating like that through the y-axis. Okay, and so in that way, now on this 2D board right here, allow me to do my best, okay, to draw that picture. But so now as my eyes placed like that and seeing down, then each stripe here, each horizontal stripe here is creating for me, as we're rotating around the y-axis, each stripe will create for me a circular cross surface again. And that's how I create my picture. That's how I create my picture. Okay, and that's how I create my solid. So this time the rotation axis is the y-axis. Okay, so the y-axis here is the rotation. That's again just a terminology right there. So any of these problems, we definitely need a rotation axis. Okay, we need a rotation axis for any of these problems. Okay, so now starting to have hopefully a little bit of an idea, right? I'm going to get back to the other board right there, and we're going to dive in even further. So general rule of thumb for now, doesn't matter if you are, doesn't matter where your rotation axis is. That could be either on the x-axis or it could be on the y-axis. Now, later on, when you get even more advanced, then you can create your own problem. But here at this stage, when we are beginning into this kind of problem, we just only need to learn how to how to rely on our own imagination and to understand the problem given from whoever the author is. So these problems is once given to us, all we need to do is we take what the description is and we put that into our imagination and then start handling the problem according to the description of the problem. So let's say the description of this problem here is that we have a curve here, and that curve makes some area between the curve and the x-axis, from a starting point to an ending point on the x-axis. And then we take that region, rotating it. We are asked, that's the description of the problem, we are asked to take that region and rotating it or revolving it around the x-axis, in this case right here. And so once we know that we're doing that kind of problem right there, then one generality, one rule of thumb here is always try to put your eyes, think about imagining that you put your eyes to look right at the rotation axis. So in this case right here, I'm putting my eyes to look straight at the rotation axis on the x-axis, whereas on the other picture where we were asked to rotate this area around the y-axis, so I placed my eye to look down, okay, and so the rule of thumb again, we always look straight, right? We place our eyes to look straight into the rotation axis. So the rotation axis will always come right at us like this. Okay? And so that's the idea right there. All right. And so now let's see what else we can think about in order to really tackle down the problem, because we just barely began. We have just barely began. Okay? But once you have a good hang out of that, you're gonna be amazed with such a huge usefulness of how we apply the definite integral into solving this kind of problem, and you will start having fun and enjoy these kind of problems out there. Okay, so now before I start tackling down the problem, okay, I have to remind you again, and I have stated this since the beginning day when I first introduced what a definite integral is, and now I will remind you that again. And any time that I'm introducing a new application of a definite integral, I will constantly remind you this before we begin getting into the problem. Okay, so what do I want to remind anyone? An integral, or precisely a definite integral, is accumulation. A definite integral is accumulation. Okay, so nail that down in your mind for me. A definite integral is accumulation. We're accumulating infinitely many small parts to reach to a whole bigger. That's our goal. Okay, and so now in this way, how do I see the accumulation to happen in this picture? All right, so now I'm gonna try to my best to retain the picture, but I have to erase all of these extra notation here, extra notes here. Okay, so now we know we're placing our eyes to look straight and right in this picture. Now I'm starting to explain what do we want to accumulate so that we can achieve this exact volume. It's not a sphere. It's not a rectangular box. It's a picture that looks round, right? Because we're rotating. It looks round. Okay, but it's not a sphere. It's not a cylinder. You see what I'm saying? So now here's the idea. So think about before we're rotating. You see the very first stripe right here can already be a good explanation, or the very ending stripe. But now allow me to choose just some stripe, and I'm talking about, think about that, back to that instance before we started rotating it. Okay, right before we start rotating it, before we even had this picture, before we even had this, because without rotating it, then the area stay fixed right there. It won't even get down to that bottom part. Okay, and so now I want you to roll back to that point, that instance, before we rotating it. Then so this area here, we can draw infinitely many stripes through that area. Any of these stripes here. I'm drawing about a few stripes already. So allow me to only focus on one. I only need to focus on one. And there's also one common generality that I want to point out here. You see, so in the way how I'm drawing, then the stripe is perpendicular, making right angle with the rotation axis. So this is the rotation axis. See, so right at that point A right here, we can cut it straight up like that to hit the curve, and we have a stripe, a vertical stripe. And vertical stripe here, I mean in the sense that it's perpendicular with the rotation axis. Okay, so we have a stripe. So just like that, this stripe here to represent generally any other stripe. It's a stripe. Okay, and so now I'm still on my way to explain what we are accumulating. Okay, so everything starts back at that point where, think about before we rotate. Then anywhere in this interval, we can create a stripe that go from the rotation center and head out there to end and hits right at the boundary where that curve is. Okay, so it goes from the rotation center, the rotation axis, out to the curve itself. The curve is here, and the stripe stops right there. So again, you have seen the idea. Back in the day, I was trying to explain about what a definite integral is. Then the height of this stripe here is short or long depending on where we're at on the x-axis between A and B. Okay, but that's just minor information. That's just details that you're supposed to know by this point viewing this video. Okay, but now once again focus on that stripe right there, and now again back to what I was trying to ask you to imagine. If you place your eyes here and looking straight at the rotation axis, you put your eyes here looking into that, and this area start rotating, then right at that stripe right there, right at that stripe, we are going to create a circular surface. I mean, it's a circular cross section. So if we're rotating it, then like all of a sudden in front of us, there's like a whole disk, to be precise. Many standard textbooks refer to that cross-section. It's a disk, because it is a disk. Right now in that picture, just take that slide, just think about it, only this pencil tip right here, and if I start rotating it right in front of the camera here, my arm right now is the rotation axis, and just this is one stripe, and I'm rotating it. And when I'm rotating fast enough, you can start seeing a disc-like structure right there. So just like that, this stripe right here, when I'm rotating it, and doesn't matter which orientation we're rotating, either clockwise or counterclockwise around our rotation axis, it shouldn't matter. But now from where our eyes is seeing it, now in front of our eyes, we will have a circular disc. Okay, or another way of interpreting it, I want to generally call that the circular cross-section. See, it's a cross-section, because now think about if you're at a different stripe right there. If you're at a different stripe, then, and once that stripe is rotated, you have another circular cross-section. Okay, another circular cross-section. And yes, you call that a disc, that would become entirely okay. And so that's why when you're at the very last stripe right here, you're also at the last circular cross-section. And when you're at the very beginning, when you are at that very beginning circular, that very beginning stripe right there, and when you're rotating it, you also end up with another cross-section. So it's all cross-section. Okay. So, and still, I didn't get to that core of that yet. But so now, again, if we just focus on one cross-section, and I have explained hopefully thoroughly enough that the cross-section, each cross-section, doesn't matter which one, but each cross-section is a circle. So take note of that. Each cross-section, okay, each cross-section is a circle, or how about a more precise term, circular disc. Each cross-section is a circular disc, because your eyes is right here looking right at the rotation axis. So each stripe is giving you a circular disc. Okay? And so in that way, so now here's how I'm seeing it. Each stripe does have a thickness. Okay? Now you must make sure to connect what I'm saying now with my explanation back in my beginning, much earlier lecture when I started to explain what a definite integral is. Then so even a stripe, even a pencil stripe that I'm making on the board here has a thickness. So each stripe here has a thickness, and once we're rotating it, it becomes a circular disc. But it's not just one. It is a thin disc, but it's not a disc without thickness. There is thickness. So each disc here has thickness. That's the idea that I want you to nail down. It's all because each stripe has a thickness. Each stripe has a thickness. So consequently, as we're rotating that, each of our cross-section, outside from being a circular disc, now we can also say each cross-section okay, has a thickness. All right, underline that for me. Okay, and each cross-section is a circular disc. Underline those two details for me. Okay, and let's see if that's true for the other picture I put on the board before we finally get into that point. And I'm still not completely done with explaining what we are accumulating yet. Okay, hold on with me on that. Be patient with me on that. And so all I'm saying here is I just want to point out all of those truths behind the scenes on any of these. So as we are putting our eyes along the right to align with the rotation center here, to look right at the rotation center, then each stripe, again, that same generality that I have explained earlier when we were rotating around the x-axis. Now if we're taking an area and rotating it around the y-axis, then each stripe here, as a generality, each stripe is perpendicular to the rotation axis. So in this case, the stripes are horizontal stripes instead of vertical stripes. Okay? And once we're rotating it, each stripe again becomes a circular disc. Okay, once you're looking down, so there, it's a cross section here. Each cross section, each stripe becomes a cross section, and each cross section there is a circular disc. So it's still exactly consistent, or it's still that exact nature of whatever I was explaining on the other board, from the other board. Okay, and again, even the pencil stroke that I'm drawing here to the stripe, to describe that stripe, it has a thickness. The thickness is about right here. Okay, I'm really attempting to make a small curly bracket to indicate there's a small change, to indicate there's a thickness, an infinitesimally small thickness. Okay, so just like that, either we're rotating our area, our region around the y-axis, or we're rotating it around the x-axis. These two truths remain exactly the same. Okay. All right, and so now hopefully at this point, after a very hopefully thorough enough, right, but explanation, trying to make viewers and students of mine to understand through the video lesson here, then at any stripe we will create a cross section in a circular disc. Okay, and then each cross section there will have a thickness, simply because even the stripe itself has a thickness. All right, and so now, again, sadly, I have to erase the extra information here. So now think about what I'm about to push into the next step right here. Then now we realize that each cross section here is a circular disc. Okay, then we can obtain the area. I mean, I'm a little too rushed. Let me roll back a little bit. Now, upon realizing that each cross section here, right in front of our eyes, right opposite from our eyes right here, right in front of our eyes, is a circular disc. Then really the stripe itself, the stripe here, okay, the stripe is, that might be a little too hard to view right there. So the stripe, another truth, the stripe is the radius. The stripe really, or geometrically, the stripe, that stripe from the center out to the curve itself, and the stripe that's being rotated to become the circular disc, that stripe, once it made the circular disc, the stripe, the length of the stripe becomes the radius of the disc. And I hope I explained another truth like that. So just like that, on the other picture, whether you are rotating around the y-axis or the x-axis, or here specifically the y-axis. I started out explaining about rotating around the x-axis, but now even when you're in the case of rotating around the y-axis, it's the same. The stripe has become, once you start seeing a disc in front of your eyes right here, then that stripe right there now becomes the radius of the disc. The radius of the disc. Okay, so now again, I'm going to switch back to my other board. And so now, if we think about it, the radius here, square of the radius, get me the area of this circular disc right here. Okay, so now here's the plan right here for accumulating. All right, so sadly I have to erase part of that work here a little bit, because I need to write down the truth right here. So now here's the thing. So we think about each disc here. Once we've had each disc, then right on each disc there's or each cross section, I'm gonna try to obtain the cross section area. Okay. So just the way it is, each cross section has an area. I mean, now once you see because each cross section another detail to mention, but I believe anyone is mature enough to see this even before I speak it out. Once you realize there's a cross section in front of you, it's an area just right in front of you. So think about, if I'm rotating this pencil through a rotation axis right in front of me, then in front of me there's a region created by this rotating pencil, and that region has an area. Okay, and so now think about the cross section area. If we can by any way obtain the cross section area, and to be a little extra note here, as a disc. Okay, as a disc, cross-section area as a disk. If we can obtain that, if we can find that cross-section area and multiply that with the thickness, okay, multiply that as a thickness. See, cross-section area, and in this particular situation, it's a disk. Circular disk, circle. I'm starting to ring up a bell right here so that you can start also thinking ahead a little bit. But now in the end, the area of a cross-section here, if we can get that area on each cross-section and then multiply with the thickness here. Sit back for a moment, think about what's the consequence of this. Again, take one moment to think of what the consequence of this product is. What is it going to give us? What is this product going to give us as we multiply the area on any cross-section, at any cross-section with the thickness at that cross-section? Say, for example, if you're looking at this cross-section created by this stripe right here, we have a thickness for that stripe. Okay, every stripe has a thickness, right? Every cross-section has a thickness. We already know that, and it has an area. So what kind of quantity do we obtain here by taking the product of the cross-section area, disk or whatever, but cross-section area, but multiply with the thickness? So in that way, here's the kind of picture I'm getting. Yes, cross-section here, but maybe there's a thickness like that. Okay, rotation axis comes out like that. Okay, then what kind of picture do we have here? We have a thin disk, but it's the volume. It's the volume of one thin disk. That's what this is. Okay, this is the volume of one thin disk. The volume of that infinitesimally small cross-section, infinitesimally thin. I should have said that. Okay, this product right here, the product between the cross-section area multiply with the thickness right here, that product gives us the infinitesimally thin volume of a cross-section. So there's this cross-section here, we can multiply the cross-section area with the thickness. There we get the volume of that one. And then so on any of these cross-section, if we can just multiply the cross-section area with the thickness, we get the volume of one thin disk. So I'm drawing it like here. So in our situation here, each disk, each cross-section is perpendicular with the rotation axis. Okay, let's see if it's true on the other picture. I really apologize for keep switching back and forth, but that's the point. I want you to understand, you know, I want you to gain that flexibility between whether you are rotating around the x-axis or rotating around the y-axis, and allow me to approach to deliver my explanation quite different from the way many textbooks and textbook authors are giving it. Okay, so again, just like that here, even when we're rotating around the y-axis, there's the disk. So once you're looking down on each disk right here, if you focus your attention to one specific disk, you can always multiply the area of the disk or the area of the cross-section with the thickness. How thick that is with the thickness. See, each disk got a thickness. And then multiplying that way, you will obtain the volume of one infinitesimally thin disk. I almost said small disk, but it's not small. It's just one infinitesimally thin disk. Okay, and that's the idea, and that's what this generality is for. Just simply for any cross section, all we do is just trying to find the cross section area and multiply the cross section area with the thickness. That already gave you the area of one thin disk or one infinitesimally thin cross section. All right, and so now the famous part that I keep yelling out loud to any of my calculus 2 students, any of my integral calculus students. We're accumulating. Okay, so we're accumulating all of these thin disks. See, this sign right here, I've done this math, this kind of work for so long to the point that I don't see this as an integral. I see this as accumulation. That symbol right here rings a sign for me. We're accumulating. We're putting little things together until we accumulate and get a bigger thing. Okay, and so now we're accumulating all volumes, all little infinitesimally thin disk volumes from a start, okay, from some starting point to an ending point, ladies and gentlemen. And that is the way, and that is the only way of how we obtain the volume of this kind of solid. Okay, so I want you, anyone viewing this video lesson, to only need to focus on this concept right there. Everything we do is, once again, simply to start out with focusing on one cross section. Okay, and in this particular case where we're rotating our region, then the cross section appears to be perfectly a circular disk that's centered right at the rotation axis. So we can obtain our area of the cross section as indicated here. So first we take them, we find out the area of our cross section, and then multiply our area of the cross section with the thickness, with its thickness. And then in that way we have the volume before accumulation operation right there. Then we have the very thin volume of one infinitesimally thin disk. And then now we're going to be accumulating from some start to some end. That's how we obtain the volume. Because think about it, the volume of the disk is small here, and then as we travel along the way, the radius gets bigger, and so the disk got bigger. But as each disk got bigger, the volume, the infinitesimally thin volume, also gets bigger. And so we're accumulating all of those up, and consequently we end up with the volume of the whole solid right there. Okay, and so just like that, right here again. So each of my disks in this way, since the rotation axis is the vertical axis for us here, then each disk is going to look like that. With I'm trying to make as thin as I can. That's a thin disk right there. Okay, and the rotation axis comes out like that, right from the center of the circle. Okay, and so now with that thin disk right there, we're again accumulating. So cross section area, and again as a disk. Okay, so on any cross section, we're going to take the cross section area as a disk, multiply with its thickness. See, that's a thickness. All right, and then we're going to be accumulating all of those volumes that's ranging from this starting point to the ending point right here, for some start to end. And that's how we can obtain the complete volume in precise value of that solid, the solid that was generated by rotating a region. All right, so it wasn't my idea who came up with this. We gotta admire how creative the past mathematician came up with all this technique right here, and pass it down on many generations down to us right here to learn this. Okay, so now that's the basic understanding and the core understanding of that. Okay, and now let's get to really, I'm going to immediately bring up an example. I mean a demonstration problem. Okay, and then we're going to do about one or two examples right here in this particular the lesson right here. And then after this particular lecture right here, I am going to produce discrete and disconnected examples as separate clips, so that the more you view, the better experience you get. But you are not required to view all of those examples, but just the more you view, the better you get. But those examples are expected to be aside from this particular lecture right here. So this particular lecture, I will only introduce about two examples where it shows the generality. And this is specifically the part where it's the more basic kind of problem. Okay, and then after doing about two examples right here in this particular problem, I should be able to make some more generalization right there, and make our way back to connect with any standard textbooks. That in case any one of you viewing this video love to read the textbook, and then you won't see too much difference between how I explain that here and the way how your textbook is indicating it. Okay, all right. So now nail that concept down for me. In order to get the volume of any of these solids that's generated by rotating a region, any region, okay? And right now I'm introducing the kind of region where it's simple, we going from one curve, right? We going from that area. The region is the area between the curve and an axis, right? And between two values, right? From a starting value to an ending value on the axis itself. And we can take either the x-axis to be the rotation axis or the y-axis to be the rotation axis. Okay. All right. So now let's look at our first example. And again, I don't need anyone when I'm giving, once I wrote down the description of the example right here, I don't need any viewer or any student of mine viewing this video to worry about, is the curve going to be a function of x or is the curve going to be a function of y? At this level of your understanding in math, a curve can be expressed either in terms of x as a function of x, or it can also be in terms of y. And it also, yes, it also depends a little bit on the domain, but that requires your understanding of the algebra. So you always have to also know your algebra pretty well on any of these things right here. Okay, so make sure to constantly get your algebra going. You gotta get your algebra going. Okay, so now let's look at our example 1. And let's start seeing how creative we can apply these ideas into our problem right here. Okay, so yes, we want to find a volume. Okay, find a volume of the solid. Okay, the solid that's generated by rotating or revolving. So it all depends on your comfortability. Some people, I was at some point comfortable with using the term revolving, maybe to make myself sound, formal, and then at some other point I'm using the term rotating. It means the same thing. Okay, so find the volume of the solid generated by rotating the region. Okay. By rotating the region enclosed, or sometimes we can word it as bounded, similar meaning. Enclosed or bounded by, okay, number one thing. The first information, the segment, okay. So, quick clarification, a segment is just a short segment of a line, so it's meant to be straight. So not bent as a curve we expect, but it's a graph. Okay, so a segment, the segment that's connecting 2 points, 2, 1 and 4, 5. So we have one segment right here. Okay, so the solid is generated by rotating this, by rotating the enclosed region that's enclosed by first the segments right here. The segments connecting 2 points, and then the x-axis. Okay, so it's the area that's between the segments here and the x-axis, and then from x equals 2 to x equals 4. Okay, so 3 description here defines our regions, and then we take, so with the 3 description here that define our region, we're going to take that region and rotate it, and once we've finished rotating it, we're going to find the volume of that solid right there. Okay, and so it's not, anyone usually, for people who learn through integral calculus, then finding volume, the kind of application is finding volume usually, I'm not saying it's always, but usually or often enough, come after finding areas, after you learn how to apply definite integral into finding areas. Okay, the reason I mentioned now is that allow me to assume that this lecture right here is maybe viewed after finding areas. After you've learned how to find area using an integral, then these terms should be familiar. Okay, and then so the term be saying enclosed or bounded, those are the term that back in the days that you viewed those kind of problems about finding areas, then you find these terms here. But then the area here is defined by, you got a segment between the segment and the x-axis, and then from some two values on the x-axis. That's why it's saying from x equals 2 to x equals 4. Okay, and then we're going to take that, but now here we're doing the more advanced kind of problem. We're going to take that area, rotating it. Okay, so now the next, so I left out one information. So now, see, main thing here is to rotate. So we're rotating this region here, but then about the x-axis. All right, so about the x-axis. Okay, and so allow me to add in some more along the thing I talked about, the areas or not areas. Now, in case you have seen or you have learned how to find areas before we get to this video, the lesson, then you might be a little threatened or afraid that we might have to decide, well, this is a little bit better than area, but back in if you were already knowing, if you already knew how to find areas using definite integrals, then for an area given at you, you can make your decision either to use with vertical stripes or horizontal stripes. And here I'm only talking to the people, to the viewers who already know, who are already comfortable with finding areas. Okay, so if you're finding just as an area problem, then you have your choice of going with horizontal stripe or vertical stripe. But now when we're into the world of finding volume kind of problem, then really we don't have that kind of situation where we have to decide to go with the horizontal disk or vertical disk. Nope, that's not the idea right there. We just take whatever given to us here and we work with that. So there's nothing for us to decide. That's the one thing that I want to also clear out right there. Okay, so in case you have already learned about finding areas and you still bringing that worry with you a little bit. Okay. And so here we just take whatever that description here and handle that based only and only everything we need is that fundamental I brought out earlier. That fundamental about on each cross section, find the area of the cross section and then the thickness, and then multiply that together to get the infinitesimally thin volume, and then we're going to accumulate all of those volumes from the start to the end. That's how we get the volume. Okay, and so now that's the description of our problem right there. So it's a little bit of a lengthy description just for the area, and then once you got the area, we take that area, rotating it about the x-axis. So the x-axis is our rotation center, is our axis of rotation. Okay, so now let's get to it. Let's get it done right here. So yes, I am going to move over to my other board. So I also need to mention as experience right here. Many times, I'm not saying always, but many times the problem due to the amount of excessive wording, it's the way it is. So many times the problems or a finding volume problem will skip asking for making a sketch. So it seems like you are not required. I mean, yes, it is true that you are not required, but it's something that's highly recommended. Okay, so even though the problem did not state at all that you got to make the sketch of the area and then rotating it, even though it's not mentioned, but it's highly recommended because just consistent with what I said earlier, you need to start triggering up your imagination. So make this sketch first. At least make the sketch of the area, and then imagine how we would rotate that area around the specific that specified axis of rotation. Okay, and so now let's look at the description of the problem one more time so that we can have a clear picture of how to sketch. So the area is here. The area, the region is the region enclosed by. We have a segment that's connecting the 2 points 2, 1 and 4, 5. Okay, so how do I see that on my other board? So think about, we have a graph system in the x and y graph system. So 2, 1 is maybe here. Okay, 2, 1. And it's a segment. Keep that in mind. So the picture here needs to be a little straight piece of a line, right? A straight piece of a line. And then here we're looking at 4, 5. So like that, 4, 5. And so that segment right there, that's what it is. Okay, and of course, again, forgive me that I can't make the best precise picture out there. In the end, I'm not an artist. Okay, I'm a math teacher. Okay, so now from 2 to 4, see? So after we get that, here's how it comes with the area between 2 and 4, from 2 to 4, from x equals 2 to x equals 4. So imagine your x-axis is here, x equals 2 to x equals 4. And then between the segment here, so we got the segment, between the segment and the x-axis. See, the region enclosed or bounded by the segments connecting those 2 points, and then the x-axis, and then from x equals 2 to x equals 4. X equals 2 to x equals 4. Okay, so with that 3 pieces of description right there, that defines our region that we're rotating. So now I'm going to go ahead and start shading the region right there. Okay, so the region we have is definitely here, the region that we will be rotating. It's here. It's that region. And now allow me to swing right by my computer to really have a precise picture on the computer screen. All right, so here's my favorite graphing space with decimals right here. So here's that little segment. And then allow me to put the grids on so that you can easily identify the coordinates. See, 2, 1 is this point. Okay, and then 4, 5 is that other point. So the segment, this straight segment connecting the 2 points. So that's right there. And now we have an air, it's in between 2 and 4. So I'm going to put in the start and the end of our interval. Okay, so that means our region has to be shaded inside of that, just like how I was shading it earlier. All right, so here comes the shading. All right, so now with that shading, we're going to be, according to the description of the problem on the board, we're going to be rotating that whole shaded area around the x-axis. Now, it doesn't matter which way you are rotating. So back on my picture that I had on my board right here, if you're looking right at the x-axis, if you place your eyes right here, okay, then the rotation can go that way, or the rotation can go this way. Counterclockwise or clockwise does not matter. You're still going to get the whole volume of a solid. Okay, and so now I found decimal is quite powerful in a sense of creating the volume, the rotation right here. So allow me to switch back to the graphing calculator, and here's in the 3D view. All right, so that's the picture. Okay, I should have made the setting to turn the shading in terms of the pink area, like how I've had it earlier. But so here's the region. Okay, so let's now observe the changes. So now this decimals here, actually it's credited to whoever, that unknown person. I only borrow their work right there. But it's a very creative work that the person made this, making it possible for me to give this lecture here. But so imagine this is the x-axis, and this vertical line is the y-axis, and there's some third dimension axis right here. If you don't have any particular experience in 3D math right there, then don't worry about what that axis is. But now let's observe the rotation. Here we go. We're having some rotation right there. All right, so there we go. That's the rotation. That's the kind of picture that we get after rotating this region, but around the x-axis. And so the author of this little decimals activity right here made that rotation to go around the x-axis in the clockwise direction. Okay, and it's even nicer that the author also prepared for me some adjustments so that I can adjust this, the 3D direction, so that we can have a better view of that. All right, so see, I can rotate that. Okay, so now that makes my view turns a little bit different. So if we place our eyes right here looking straight at that, then we can see kind of like a truncated cone right here, some truncated part of a cone right here. All right, see, and if we're looking away right there, that's the look of our solid right there. Okay. All right, so now once we've had an idea right here, I'm going to get back on my other board and let's really handle it. And so now we really just need to go back to the original region before we rotate to think about it. So now, again, imagine that we place our eyes right here alongside, right along with that rotation axis. And then now if we think about, we make any thin stripe, any stripe inside of the region from the rotation axis out to the curve that defines it. Because here's start and here's end, we already kind of had an idea. The picture itself, so you gotta, that's why I said start triggering up your imagination and your sense about observing picture. Okay, we gotta get that kind of skill down. I mean, we are gifted with having the eyes right there so that we can look at things and decide. There are things that it's so physical that we have to learn how to look at it. Okay, and so there's a stripe, and we know that the stripe has to be, from that generality I mentioned earlier, the stripe is perpendicular or 90-degree angle with the rotation axis. And so now as we place our eyes there, and then imagine that if this stripe is rotating in front of our eyes, then we are having a disc. Okay, we're having a disc, a circular disc. Okay, and so now it's easier as a most common practice right here. This is my own experience. It's once you see the disc, the first thing to decide, because remember, all we need is to know the cross-section area. And then once we know that cross-section area, then we will multiply with thickness. Okay? And then once we set up the product between the cross-section area and the thickness, we're going to start accumulating from a start to an end. Okay, so now sort of like a lot of steps are here, but the first step in my experience allow me to pass this down to students or viewers who are viewing this lesson right here. I see it's, for me, at least for me personally, I mean personal experience, easiest here is to get the thickness because it's consistent right in the way how the picture is being seated. Your disc is facing you. Your eyes are right here, the disc is facing you. And the disc is, rule of thumb, is always perpendicular with the rotation axis. The disc is perpendicular with the rotation axis. And in this case right here, since our rotation axis given to be the x-axis here, then so the thickness has to be an infinitesimally small change in the x values. So now just write it down, list it down. Be organized. Be neat, okay? Thickness listed in this problem as dx. All right, so now it's where we apply our calculus understanding right here. Thickness is a change in x value, but being infinitesimally small. So that's the differential dx right there on the x-axis. Okay, and so now keep that in mind right here. But you see how this is how things connect to everything we have learned back in the very beginning day when I first delivered my first lecture over here. Once we have decided the thickness here being the dx, then later on when you found some clue regarding how to find the cross-section area, then we have to express that cross-section area here as a function of x to be consistent with this d differential over here, with this d expression. Okay, and so now from first step is to get the thickness. So now step 2 right here is to get the cross-section area. Okay, cross-section area. Okay, so now cross-section area, here's how I'm seeing it. Cross-section area. Okay. Of course, we know it's the shape is a disc. Disc. Circle. What's the formula for area of a circle? Anyone knows it? Anybody knows it? Area of any circle is pi r squared. Okay, and so of course we have to bring in some common understanding. Okay, we have to bring in some common understanding, but believe in yourself, you know the stuff at the moment you are viewing this video. Okay, so area of any circle is pi r squared. Pi r squared. What is r? R is the radius from the. If you have a circle, radius is from where the center of the circle out to where the circle is, out to that line on the circle right there. That's the radius. And so now in that way, pi r squared is the area of the circle, the area of each disk, which is each of our cross section in this case. So the area here I'm seeing, that means this is now my radius. My radius, just simply the height of the stripe here. And right now, just like I said, again, focus right in the way how we place our stripe. It's not really our decision. Whoever gave us the problem decide for us that we're rotating around the x-axis. So it's not our decision. But once we understand that description, then it has to be as a generality that the stripe here, the stripe that once rotated, create a disk, that stripe becomes the radius. That stripe becomes the radius. So in the way it is, then this stripe here we have to, and this stripe starts from the rotation center, from the rotation axis, and stops on the curve itself. The stripe comes out from the curve, from the rotation center, the rotation axis out to stop at the curve itself right here. So that means we have to express this curve here. Now we have to find a way to express this curve here as a function f of x. We now have to, because I purposely brought up this problem. It seems a little unusual at first, where it makes it kind of throw people everywhere. But a segment connecting 2 points, with a little bit of experience in algebra, you can see that this same segment right here, you can write this segment, the equation that represents this segment as a function in terms of y, or you can write that equation representing this segment as a function in terms of x. You have your choice on that. So now we properly made our choice to reflect the situation we need. So the situation we need here is that since the stripe here has to stand vertical or perpendicular with the x-axis, so the way we measure the height here has to be a function in terms of x, because the stripe here is the height that goes from the rotation axis out to the curve itself above it. And so definitely we have to indicate that height as to be the function's height at any instant x. Okay, so x is some instance here. So at different x value we have different height, but this is now the radius. So I already labeled that f of x here is this curve, so have allowed me to now indicate this short section right here is our radius. That's all right there. Okay, all right, so now we clearly see that we have to express this as f of x, as the function f of x, same curve, but as a function f of x. And so now I'm going to write that as, we need f of x. At any x instance, I'm going to square the height of f of x, because that's our radius. And so area of any circular cross section here is pi times radius square, so pi times f of x square d. Okay, and so now pi times f of x square dx, and then particularly for this particular function, now with a little bit of algebra, you can see that this segment here connects these 2 points, and it appears to be a line. It is a line. It's a segment, so it's a line. So line has equation in terms of x, famously mx plus b, y equals mx plus b. That's what this line is. Okay, and so now allow me to treat this kind of like a scratch work right here, but quickly slope here of that line has to be, for this line right here, it has to be 5, which is the rise over run formula right here, 5 minus 1 over 4 minus 2, that gives me the slope 2. So my equation for the line, so with that slope right here, now allow me to quickly erase that. So equation of a line has to be sum 2x plus b already. Okay, and now I know that this line contains the 2 points here, 4, 5 or 2, 1. Again, just a brief algebra review right here. Take either one of the two coordinate values here, take either one of the pairs here, substitute that into the current halfway done equation, X for X, Y for Y. So I'm going to choose that one right here. 2, 1, because simply the values are smaller. So 1 equals 2 times 2. Okay, plus B. Now we're on our way ready to solve for B. So B equals minus 3. Okay, and so now that means this segment here can be expressed as y equals 2x minus 3. 2x minus 3. And now 2x minus 3, that means we can also write that as f of x is a function in functional notation. F of x is 2x minus 3. That's how I'm seeing it. That's how I'm seeing it. So that means now consequently into this problem, the area of each cross section is determined or is governed by pi, by the formula pi times 2x minus 3 square. Okay, 2x minus 3 square. And so now in that way, then we are ready to make that final step right here. So now once you got the cross section, allow me to erase some part of the work right here because, or actually, I'll work it on right here. So just in that fundamental I pointed out earlier, we need area of each cross section. Now we know it's this, so it's pi times 2x minus 3 all square. We need to multiply with thickness. Now it's dx. Now you can all see how things are consistent. Back in the first day when I even start introducing about even antiderivative stuff, see, the d expression in our integral has to always be consistent with the variable's name. And see, so that's why usually in my first step, in my own experience, first step is to decide the thickness, because the thickness will reveal for you immediately what your d expression is. Is that a dx or a dy or a dv or d whatever? But once we've had that, then that drives your decision into deriving your just one same curve, but you can either write it as a function of x or a function of y. It all depends on how you see this d of yours right here, this d expression of yours. Okay. And so now clearly it's, once we chose it dx, we write our function here, our area function as a function of x right here, making it consistent. And now this product here between area of the cross sections with the thickness here is enough for the volume of one infinitesimally thin volume. And then now we're going to start accumulating from start to end. All right, and so again, allow yourself to view the picture and find out for yourself. And it should be easy. Trust on your own natural sense right here. In the way how the picture starts like this, on the x-axis, where should it be? And see, it's all about, so why is it start and end on the x-axis? Why does it have to be start and end on the x-axis? Because our stripes are on the x-axis. We're accumulating along the x-axis, along this rotation axis right here, which happened to be chosen by the problem to be the x-axis. The x-axis chosen as the rotation axis. Okay, and so now that means I'm accumulating from start to end being 2 to 4. That's my start to end. So now all of a sudden I successfully set up my integral problem. All right, and so once we have our integral successfully set up, the rest of the work here is just simply to treat this as a definite integral. It's a definite integral. And then once we set that up, we feel free. And of course, so at this point, needless to say, this lesson here should be learned after you have already learned about the fundamental theorem of calculus. That's why, anyone who already has viewed my video lesson for fundamental theorem of calculus, it seems like I always emphasize the importance of Isaac Newton, who came up with the fundamental theorem of calculus, because it opens a door for us to apply all of these his work into all of our work here, finding volumes, finding all kinds of work. Okay, and so now here we go. We already had our volumes successfully set up as a definite integral. Now notice for ourselves that pi here is a constant, so we can put it in front of the integral as a coefficient. And so continuing into the next step, and so now that would simply just be, and at this point, allow me to erase this here. because I need more space to advance on my board. All right, and so now what I am going to have pi being put in front. It's an integral from 2 to 4. Okay, and now we can algebraically FOIL out that square here. So that's making it 4x squared and then minus 12x plus 9. Okay, with that dx expression. And so now things looks just like any ordinary definite integral out there. Okay, and so now in my next step again, and now I'm having more space down here, so I'm going to start writing in this longer line down here. So equals pi and one more. So now pi, and then here I'm going to start taking the antiderivative term by term. So it's going to be 4/3 x cubed minus 6x squared plus 9x. All right. And then fundamental theorem of calculus says we need to evaluate this from 0 to 4 like that. Okay, so now at this point again, like as I said, the fundamental theorem of calculus should be the idea. So allow me to skip that showing the calculation step. All I'm doing is in my next step I'm just showing the substituting in step right there to make our work concise right there and to make sense. But I don't really have to show every stepwise, and I'm going to step out to my calculator on the computer station to get that numerical value. So here we're looking at pi times 4/3 times 4 to cube power minus 6 times 4 squared plus 9 times 4. So that's my antiderivative evaluated at the upper limit, and then I'm going to subtract, and then now it's a pi, and then here it's again it's another 4/3 times 2 cube minus 6 times 2 squared plus 9 times 2. All right, and so now I'm going to quickly step over to my computer station to get a final numerical outcome, a numerical answer for this. All right, so my numerical calculation came out to be, my computation on the computer came out to be, with after all that subtraction and doing the calculation work, and I'm going to keep that in exact expression with the pi leaving it in exact expression. And so I'm looking at 62. So my final answer came out to be 62 pi over 3. All right, 62 pi over 3. And that's going to be the final answer for this, the problem here for this volume. So the volume looks like, all right, so quickly back on my Desmos calculator, then the volume of this truncated cone right here has that volume 62 pi over 3. Okay, and that came out from rotating that region around the x-axis. All right, and so now as we have reached the end of this example, let me now make some connection with the way how many standard calculus textbooks have been delivering as a formula. Okay, so for me, in the way how I explain this to my students, I want my students to focus on that core concept where I introduced earlier. It's the area of the cross section, multiply on each cross section, multiply with the thickness, and there we have a little thin volume. We're accumulating all of those volume from a start to an end, and that's how we get the general area. I mean general volume. Okay, but now in the end, if we roll back to this, so the solution to the problem is done here. All right, and so now, so I explained hopefully thoroughly enough. That the reason why we have to change this curve, because the curve here can be written as a function of x or a function of y. Okay, but so I hope I gave a thorough explanation enough of why we have to. So that's the part where we can decide right there. So we start out by identifying our thickness, and because we had a thickness, we have to drive our decision into choosing to express. So we have to express this curve to be according to the D expression after we got the thickness. Okay, and so now, so many textbooks write a formula as following. It could be a little dangerous if you're only reading the textbook and without trying to think deeply into that. So many textbooks deliver the formula that, hey, if you have a region like this, right? If you have a region like this, or generally speaking, we have a region and then between the curve and the x-axis, right? And then between an A to B and rotating the region here around the x-axis, just like the problem we just did right there. Then if we have something like that, then many textbooks just get rushed straight into then the volume formula. See, when we know the volume formula here is from A to B of pi times f of x squared dx. This is the formula commonly seen in many calculus textbooks. Yes, it's the formula. As a matter of fact, I also explained this was, we saw this part when we were on our way deriving our area of each cross section. Okay, but now I want you to understand, reading textbook is one thing, but you got to try to understand the broader impact of that. So the point here is that, see, that is the thickness. And the first reason, in the way how I see it, the reason we use the dx here is simply because we're rotating around the y-axis, around the x-axis. So each stripe here has to be perpendicular with the rotation axis. In this case, the x-axis, and that is consequently the reason that leads to having our expression here being the dx. And for that reason, the same curve here must be expressed in terms of as a function in terms of x. And that's how, and so now area of a circle is a pi times radius, and that stripe right here as a height of the function at any instance x value, so it becomes the radius. And so in that way, pi times radius square gives us this formula right here, and that's the formula that in these days anyone will be seeing this formula in many the calculus textbooks. Okay, so but as I said, reading the formula is one thing, but I want you to understand, because anyone viewing this video lesson is a calculus student, and you are ready for applying calculus and especially the integral understanding into much more applications outside of just finding volumes and these geometric figures right there. So be ready to understand where these formulas come from. Okay, so that's how I clarified about, see, instead of myself, you didn't see me rush into immediately giving out this formula right here, but I want you to focus on the concept, on the fundamental, and then from there we make our way back and see how it's perfectly consistent with the formula introduced in the textbook. Okay, and so now another note just specifically about the problem we just did, and about any, actually this note I'm about to say is specifically about any volume problem. Okay, because in the end we use a definite integral as a tool to find a volume, but in the end a volume must always be positive and not even a zero value. So any volume has to be a positive value, because it's a volume, it's an actual quantity that we can measure. Okay, it's an actual quantity that we can measure. And so the reason I'm saying this, because you see, we can easily make mistakes sometimes in terms of our calculation. And then back in the days when I first explained about what a definite integral is, I made it clear that a definite integral on its own is neither an area, neither a volume. We only use area as a way to represent graphically the concept of a definite integral. But in the end, definite integral, the result of a definite integral can be negative sometimes. But here, since we only use definite integral as a way to find a volume, so we have to always keep in mind, expect for ourselves that the answer in the end has to always be a positive quantity. Okay, and that's another remark, or another an important note I would like to make for anyone there. Okay, so for any reason that you work your problem out and you end up with a zero volume, that doesn't make sense, because it's a picture you're seeing right there. Okay, or for any reason that you end up with a negative volume, that's completely nonsense right there. You got to go back and check your calculation work somewhere here and there. Okay, all right, so now I believe we are ready to push that exact fundamental into the same problem here, but in a different situation here. And now I'm going to call that example 2. I won't have to erase the entire example at all. I'm going to call that example 2. And so that's the reason why I've been keeping this on the board for the whole time, right there, explaining through this lecture. So, example 2. Find the volume of the solid generated by rotating the region enclosed by. So we're still using that same segment. We're still using that same segment connecting the 2 points 2, 1 and 4, 5. But then now it's the area, the region enclosed between that and the y-axis. So allow me to switch from that to the y-axis, okay? And then we're going to be rotating that region around the y-axis. And actually here I'm also going to change. I must also change from y equals 1 to y equals 5 here. Okay, from y equals 1 to y equals 5. All right, and that rotation around the y-axis. So our rotation axis here is the y-axis. That's that vertical axis. Okay, and so now before we get started, again, I want to emphasize that the problem did not ask us at all to draw the sketch, to make the sketch, but it is highly recommended that make the sketch so that you can start making your imagination. Okay, so here we go. I'm going to get to the other board, and we're going to be making some sketch. All right, so here's my sketch again. All right, so 2, 1 is here. Okay, and 4, 5. All right, so that's a segment. But now the problem now in the description of the problem, we're talking about this curve. See, the same physical curve. The y-axis is here, the x-axis is here. It's just the problem chose for us. The problem stated clearly that we want the regions between the y-axis and this curve, the region enclosed or bounded by this segments connecting the 2 points, and see, this is 4, 5, and this is 2, 1. Okay, and the region between is here. All right, and then between the y-axis and the region, the y-axis and the curve, or the segments, and then from y equals 1, this is y equals 1, so it makes clear sense that y equals 1 to ending at y equals 5 here. Okay, so allow me to write this a little further up here. So y equals 5 is right here. So now that's the region we're looking at. That's the region we're looking at. All right, and so now in that way, so once again, rotation axis is here, and we're going to be rotating that around the y-axis. That means the picture is going to go this way. Okay, orientation does not matter. Going clockwise or counterclockwise does not matter. But now imagine that if we take a slide, and yes, again, the generality here is that we have to place our eyes. We put our eyes to be aligned with the rotation axis, so that each stripe, once we're rotating it, so each stripe will be facing right at us. Each stripe will become a disc that's facing right at us. Okay, so the disc, and now we're going to have a shape like that. Okay, y equals 1 and y equals 5 up here. All right, so at each stripe right here, and so just like how we were doing in the other case, the stripe at start before the rotation, the stripe has to be perpendicular or 90 degrees with the rotation axis. So the stripe is here. Okay, and then in that way it's easier to identify the thickness and all that. All right, so now once you already had some hang of it, it's going to be a lot easier to pick up pace now. Okay, so just like that, I need to go, well, volume is accumulation from start to end, right? What I do here is cross-section area. each cross-section area multiplied with the thickness. Okay, each cross-section multiplied, each cross-section's area multiplied with thickness. There we have the volume of one disk. So our disk here is the sideways disk like this, the disk that's facing up. So imagine the accumulation here is going to go as we're stacking up the disk from the bottom up. So start to end in this sense here in the way how the picture is. It's just the way how we're looking at the picture is telling us that plan like that. Okay, we're stacking up from bottom up on the disk. And so in that way, here's how I'm seeing it. Cross-section area multiplied with thickness. Just like that experience that I already mentioned. Get the thickness first. It's easy to identify that way because in the way how we place our stripe, in the way how we place any of our stripes, it's already so clear. My picture is starting to get a little too much, but I can erase some of those minor stuff like that. All right, the stripe is here. That's the disk. Okay, so that's why now first step, let's nail down what the thickness is. So in the way it is, thickness has to be, in this case, rotation axis is here. Thickness is the infinitesimally small change in y value. Y value from a lower y to an upper y. So thickness here makes sense to be a dy, that infinitesimally small change in y right there, or it's the differential dy. Okay? And so now, and once we've had that, then it's a dy. So that means, now allow me to derive on the go. How's that? Derive on the go. So we still don't know where start and end is. So let's just write it like that. Start to end. Start to end. We still have not derived cross-section area. Let's leave it like that. Let's leave it as a general idea right here. Cross-section area, and then thickness now is dx. Dy. And so now once we clear with the thickness, then that's making it clear that we have to express the cross-section area here as a function of y. However we're doing it, we have to end up with a function of y. That's the decision line right there. So it's not really much of our control, but we have to go as the consequence of whatever comes out from the picture description. And then from what we do here, after what we recognize, the thickness must be consequently the dy in this picture, in the way how the picture is. Okay? And so now let's look at the cross-section. Okay? So I try to divide the problem into main stages so that it helps anyone. So cross-section area. All right, so let's underline that. So now again, the area again is the area of a circle. As we place our eyes in looking down, yes, it's a circle as we're looking down on it. Okay, and so in that way, with the circle, it's famously pi times radius square. Any circle is pi times radius square. Okay, any circle, doesn't matter if you're putting the circle like this or you're putting the circle in front of you. It's always pi times radius square. Okay, so pi times radius square. But now let's look further into how we can express our radius, because pi is already a constant. So what matters here is how do we express the radius. And again, the radius here comes out as a stripe. The stripes always go from the center of rotation out to where it stops on the curve. Remember, the region here is the region between the axis here and that curve, right? The curve is just a curve. But now we treat that y-axis here as the rotation axis. That's critical right there. So the stripes always go, yes, perpendicular with the rotation axis as a generality. You have already been told many times. And then it goes from the rotation center out and stop at the curve, at the defining graph like that. And so in this case, we have to express this graph here. It is now crucial that we have to express this graph here as a function of y, as an expression in terms of y. Okay? and apparently and clearly speaking, that space right there. How much space right there? That's your radius. So radius get bigger here, radius get smaller here, radius gets even smaller down here. Okay, that's how it is. All right, so now in that way, let's track down the radius. I have to erase some of that stuff right here so that we can think about it a little more. So now if we are thinking of our equation here, it has to be x equals some slope my plus b right here. I mean, any line, doesn't matter if you're expressing that as a function of y or a function of x, like in the previous example right here, but it's always have to be, it's a line, so slope times y plus b, okay? But now it's a little bit out of what we are comfortable with. Or here's one thing. I mean, I'm just pointing out as many options as possible. I mean, one direct option. Think of this slope right here. If we're treating our equation if we want to express our equation in terms of y as a function of y, then the slope formula does change a little bit. That's why I'm using different slope, capital M and B right there, and capital B. So directly, here's how it works. You can go M equals, so it's still the slope formula, but now it's going to be changing x over changing y. Be careful. Usually, yes, I understand. Usually it's changing y over changing x, delta y over delta x. But that is simply because we're more comfortable with expressing things as a function of x. That's why changing x is in the bottom and changing y is on top of the slope formula. But now, be careful. We want to express, it's just an algebra thing, but I'm not sure whoever viewing this video have seen this in the past or have had this explanation in your past algebra course or not. So I want to spend a little bit of time explaining that. So in this, and of course the reason I'm going with this direct step right here is because I'm assuming that we can treat example 2 as a completely one independent problem. That pretend that we're working on this problem without ever done example 1 at all. Okay, then with slope you have to go with changing x over changing y here. Okay, so it's x2 minus x1 over y2 minus y1. That's how I'm seeing it. The coordinate system stays the same, but if the same curve right here, if you want to express the slope, then you want to express the same line here in terms of y, then the slope formula has to go changing x over changing y. Okay, and so now that means we're looking at, so as far as the slope right here, changing x is going to be 4 minus 2, okay, over 5 minus 1. That's how it happens. Okay, and then that gives us 1/2 for slope. All right, and once you found slope, again, just use the coordinates pair, plug it in, x for x, y for y. And by the way, so that means your equation here is halfway done. X equals 1/2 for slope times y plus b right here. Slope times intercept. It's x-intercept this time, instead of saying y-intercept. Okay, slope and x-intercept. Because our function here is, I mean, we want to find out where this is crossing on the x-axis. That's why this is x-intercept. Okay, and so now, well, I picked 2, 1, but 1 is substituted for that, and 2 is substituted for x. It's still x for x, y for y, but we have to substitute appropriately. So 2 equals 1/2 times 1 plus b, like that. Okay, 2 equals 1/2 times 1 plus b. So that leads to, okay, so now we can solve for this, and that leads to b right here. The x-intercept here has to be the 3/2. Okay. All right, so that means our equation is finalized. X equals 1/2 y plus 3/2. All right. So that's one way we can directly. Derive the equation of this. Same segment. The reason I keep saying it's the same segment because it's that segment connecting the 2 points here. But now if we have just expressed that in terms of y as a function in terms of y. Okay, so that's the direct method right here. And as I said, tentatively, I gave this direct solution because I want viewers to see that in case we're looking at this problem as a completely independent problem without solving problem, without having solved, without having done example 1 prior to this, then this is the way how we're doing that. Okay, but a little bit longer route, but that means we see this problem after. I mean, if we are in that situation that we're working with this example after we have seen how we express this curve in terms of x, then we can have another alternative. This alternative is a little longer but easier. This alternative is a little longer but easier. Why don't we just write that same curve here in terms of x, just like how we did earlier? Y equals 2x minus 3. That means pretend that we have already seen this same problem in example 1, that we have done example 1 already. That means, and then after example 1, we know that the same segment right here, we can express that as 2x minus 3 as a function in terms of x. And then once we've had that, then we can apply our understanding of finding inverse function. Because the same function here, but the same curve here, but already expressed in terms of x, but we want to express that in terms of the other variable, then we just think of that as the inverse function. Fancy term. Just think about we solve for x in terms of y. Solve for x in terms of y as an expression in terms of y. So that means I'm going to add both sides with a 3, so y plus 3 equals 2x. And I'm going to divide both sides by 2, okay? And that will lead me to x equals 1/2 y plus 3/2. The two works here exactly agree with each other. Okay, so you got, this is a different alternative, but you have to spend your time, of course, like I said, I started out at that point assuming we already had that equation in terms of x, but if we're starting out from scratch and you chose to go this route, then you have to spend your time finding that equation in terms of x first, and then work around. Or you also have a choice of writing this equation here, writing this equation as a standard form right there, which, at this point right here, allow me not to go too far back into algebra. Okay? So in the end, see, the equation is the equation. And then now we've got what we want. We express the same equation here, but in terms of y now. All right. And it's all due to the fact that our thickness here is indicated as a dy expression. So now that means each radius here at any y value, each radius here is a 1/2 y plus 3/2. So that means back to the area. So area here has to be a pi for circle, pi r square, but r now is this much expression. I mean, this expression here is for r at any y value on the y-axis here between this bottom and that upper point right there. That it's going to be a 1/2 y plus 3, okay? I mean plus 3/2. 1/2 y plus 3/2. All right, and we square. That's how we generated our the area as a function of y. And now allow me to erase this. All right, and so now on the work here that we are on the way right here, then after the dx expression, so here our cross-section area, here's now how I'm filling it in. All right, so now it's going to be pi times 1/2 y plus 3/2 square. All right, so now the last step here is to hunt for where the accumulation is going from. From where and ending at where. From where is the start and where's the end of that accumulation. So that accumulation on the y-axis is given to be clearly given. Y equals 1, and it makes sense that the y value, low y value is 1. High y value is at 5, so even without telling, we can also tell. We can also tell that. Like I said again, trust your own sense about observing the picture. And when you're taking calculus, at some point you have to overcome that fear about you're not a visual person. I mean, of course, in case you are not gifted, but practice makes it better. Okay, practice will make it better. Okay, so never blame yourself for not being a visual person, and then we just back out of these problems. As long as you can still open your eyes and see something in front of you, you can start thinking about that. All right, I hope I gave some encouragement to anyone who feels a little, having a little fear with yourself, not a visual person. Okay, and so now, so the start here is clearly 1, and the end of the accumulation is 5. All right, and now that defines our volume setup for that. Okay, it defines our volume setup for that. Okay, and so now once we've had that, I need to erase all this laid down stages right here and getting ready for with all that space to do our definite integral. At this point, it's completely a definite integral. Okay, so we just take our usual work right there. So in my next step, I'm going to pull the pi out front. Okay, it's an integral from 1 to 5, and I'm going to start foiling out that square right there. And now we realize that everything is in terms of y, and it's perfectly consistent. The d expression here is dy, and the function is expressed in terms of y. Okay, so now we're looking at a 1/4 y squared plus, okay, and then the 3/2 y plus 9/4. All right. So it has some fraction involved, but that's okay. It's still an easy problem to handle so far. Okay, and so that means in the next step we have pi times 1/12 y cubed plus, and now it's going to be 3/4 y squared plus 9/4 y. All right. And then from there we are, according to the fundamental theorem of calculus, we're going to evaluate from 1 to 5 like that. Okay, and so I'm going a little loosely. Yes, initially I plan to have this problem treated independently. So if this problem really was an independent problem without seeing example 1 previously, then we have to do all the calculation work. But all right, and so now the answer comes out to this. Similar to example 1 that I've done earlier, it's now just the next step is to substitute in the two values, but I'm short of space, so allow me to just step to my calculator at the computer station and get that answer, and I'll just write the answer here. Okay. All right, so after a calculation, after the next step of the fundamental theorem of calculus, the final numerical answer should be 112 pi over 3. All right. And so now, again, it's a volume. So I should expect that it should be a positive amount like that. Okay. And then now, we cannot assume that this volume is going to be the same volume with the other one. Okay. And you can see that in terms of the drawings right here, the earlier example, the cone was much more wide open, right? And the truncated cone was a lot more wide open, whereas this truncated cone is a lot less open like that. Okay, and that's the idea with this problem like that. Okay, and so let me do a quick little demonstration of this particular picture here on the computer, but Desmos unfortunately doesn't have an activity for this, so I'm going to have to use a different demonstration right there through the web as still. All right, so here on this graphing space of mine right here, okay, with this graphing space of mine right here, then the software that I'm using here, the program I'm using here, this is with GeoGebra. So we have a 3D graph, and this is the green axis here is the y-axis, and the red axis here is the x-axis. Okay, and so that's how it's run right there. And let me make some adjustments. All right, so the area that we are shading would be inside of this space right here, and of course the x and y system, the x and y graphing system now with the third axis now is sort of like on the floor right here. So this is our graph right here in that view, and now maybe let me drag that a little bit. All right, to make it stand up a little more so that anyone can see and understand a little better about the situation. Okay, so here's our shaded area that I've made on the board earlier. So now we're going to be rotating it. So rotating that now from, see, and it's our GeoGebra already made the intersection, the start and the end of our accumulation y equals 1 and y equals 5 are all here. Okay, so now here's the rotation. All right. So as that keep happening, and we have that cone right there. All right, so that's the cone that we're looking at. All right. All right, and so now after we have done example 2, so I would like to point out another generality to make our work consistent, with how the many textbooks are giving as a formula. Okay, but again, I highly recommend that my students or viewers who are viewing this lesson right here to focus more on this fundamental rather than relying too much on the formula, because staying too much with the formula will be dangerous sometimes. Okay, because you will lose that flexibility about application, about applying the work right there. Okay, so now many textbooks deliver the formulas that anytime you have a region and you're rotating that region around the y-axis, okay, so then it comes to the formula from C to D, right? And then the pi times some function g of y right here. See, our function now is expressed as a function of y, but that's now is acting as our radius function. So pi times radius squared times dy. Okay, so seeing the formula is one thing, but I want anyone's learning from this lecture over here to understand the whole reason we have that here simply because we have that fundamental cross-section is a pi r squared, okay, and multiply with the thickness. And see, I explained that it's better that we obtain thickness first. And so in the way how it is, we're rotating about the y-axis. So we need to, thickness has to be dy. And that is the reason why we're setting up our function here in terms of y function. Because otherwise, if you only rely on, so now I really try to focus that if you can focus on this fundamental, then there's only one fundamental. But if you rely too much on formulas at one point, when you're taking exams or whatever, when you're taking a math exams, and even if your instructor, including me, allow you to use a what's so-called a cheat sheet or a formula sheet or whatsoever, you're gonna still have, you already have 2 formulas to memorize. And believe me, we're only 1/3 of all of those problems that worked with that apply finding volumes into, apply finding and using the definite integral into finding volumes like that. And so you definitely don't want to memorize volumes. You definitely don't want to memorize formulas. So know this one fundamental, and you should be able to be flexible and make your own formula when you need to. Because formula here is just if once you see this formula, it will tend to make people think that's the only case right there. Okay, and once you've learned enough cases, then there are going to be way too many formulas to remember. All right. So now, at this end right here, at this point, after finishing 2 examples, we are about almost finished with all of that work. And so now I would like to make another remark right here, another generality. And all right, and so that remark that I was about to say earlier is that, so now the method that we used here in throughout the 2 examples we have done in this particular lecture here, and the method specifically being taught in this lecture here, many textbooks and including many mathematicians worldwide regard to this method as the disk method. Okay, so everything we've been doing so far is being regarded as the disk method. So you can see that in my style throughout the entire lecture, I did not mention this name much because I want you to focus on the fundamental, that generality. So what was in the method here that led to calling this method here the disk method? So that was simply because, again, imagine we have a curve. Throughout our kind of problem here, we have a curve, and then we restrict that curve in between a certain start and end, and then we make the curve here makes an area with a given axis. Let's say, for example, in this case, the x-axis, for example. Then we have a region bounded by the curve, one of the axes here, and then between an interval, inside an interval of value on the axis there. And then we're going to take that axis itself there to be the rotation axis. And so once we have had that region defined, and then at the point where we are rotating that region, then see the stripe that I was giving explanation throughout the entire lecture, like that any stripe here needs to be that's required to be perpendicular with the rotation axis. Once we rotated those stripes, when we rotate any of these stripes, then we're going to create a disk. And then, of course, just like how I have been explaining, then we place our eyes to look straight into the axis of rotation, right there. And so in that way, in front of us is a whole bunch of disks, okay? And so extracting out each of the disks as a generality, then each disk here has a thickness. So see, there's a thickness on the disk right here, okay? And so that's referred to as a thickness. And each of the disks here has thickness and has area of the face of the cross section that's facing our eyes right there. Okay, so the cross section is facing our eyes, and then on the way how we're placing the disc right here, and the disc again came out because we are rotating that stripe, which is perpendicular to the rotation axis. So in that way right here, the disc as a cross section, or the cross section in front of our eyes right here is a disc. And we're accumulating those disks. Each one of the disks has a volume due to thickness multiplied with the area of the disk. And that's why accumulating those, obtaining the volume of this rotated region is the same, is nothing but just accumulating those disk volumes from a beginning to an end. And that is the reason why this method here specifically was regarded as the disk method. Okay, and so another point I would like to remark right here, another point I would like to remark now that, so here in this particular region, then we are rotating that region around the x-axis, okay? And so in this case specifically, when we are rotating our bounded region around the x-axis as a chosen axis in the problem, then the disks are being accumulated sideways, but from the left to the right, because remember the fundamental I mentioned throughout the entire lecture here is that we're always going to be accumulating from a start to an end. So there's a start of our accumulation, there's a beginning of our accumulation, and then it will come to an end of our accumulation. So start is on the left, okay? So that's another generality to remember. That's another key point to remember. We're always going to be accumulating those disk volume from the left to the right, in case where in the specific case where we are rotating the region around the x-axis. Okay, so in other case, what if we're in that scenario where our curve here defines an area with the y-axis, okay, with the y-axis. So we have an area defined like that, and here's our area, and if we would take that area and rotate that around the y-axis in this case, so here's the y-axis, okay, and we place our eyes looking down. We place our eyes up here looking down at the y-axis. So this time if we're looking down, the y-axis is coming right at us right here. Okay, then in that case we're still producing the disk because of the stripe. As we're rotating the stripe, we're still producing the disk facing us. So it's a different setup of the disk method. It's a different orientation of the disk. So in this case right here, since we're rotating around the y-axis, then the disk is going to look as following. It's a horizontal disk, but still same generality, perpendicular with the axis of rotation, okay, or with the rotation axis, and then it has a thickness, okay, and then of course the shape of the cross section here is a disk. That's why we're accumulating those disk volume. Then we regard to that generally as the disk method. But this time right here, since those disks are, the accumulation work here is physically sort of like the stacking up of the disk. Stacking up of the disk. I'm using that term, that hopefully daily language, enough term right there, but we're stacking up the disk. So in that way, accumulating all the disk volumes in the case where we're rotating our region around the y-axis, then the start would be, this is the start, and this is the end of our accumulation. So it makes sense that start is at the bottom. Okay, we are accumulating from the bottom up. Okay, from bottom to top right here. Okay, so again, that's also one generality to remember. If we're rotating a region around the x-axis like this, and we have identified for ourselves that we're working using the disk method, then we need to think about accumulating the disk from the left to the right. Okay, and then in case where our region bounded by a given curve with the given axis, and between a start and an end, and then we're rotating that around the y-axis specifically, then those disks that we produce will be the one that as we are accumulating, we're going to be stacking from the bottom up. So the accumulation in this case here is from bottom up when we are rotating our region around the y-axis. Okay, so it makes some slightly different between the cases like that. All right, so that's the reason why the method here is called the disk method, and I'm trying to make it now at the end of this lecture over here. I'm trying to make that consistent with how it's been mentioned throughout many standard calculus textbooks, and as well as among many calculus professors. Okay, and so now there's a couple other key generalities that I would like to point out. Some of those you have already heard as well throughout our previously discussed throughout the earlier part of the video that you have heard me saying it, and now I would like to point out or readdress those again, and also point out some other the key points right there that will help your imagination and to make it consistent with the disk method. Because at times later on, these kind of problems will become challenged, especially after I will be later on introducing more methods to handle to find the volume of those solids that are generated by rotating a region like that. Then later on when you will be learning a lot of different methods, at some point you will be confused. Okay, so allow me to bring up a few key generalities so that it helps you clearly distinguish for yourself where it is to be the disk method and where it is to be the other method, or where it is to be not the disk method. Okay? All right, so I'm going to have to erase this picture that I'm drawing. All right, so now in the disk method specifically, then this is a generality that I have already mentioned. So now we have our region. We have our defined region, and yes, all of that description was given earlier in the general discussion. Either we have a curve restricted between a starting end and an ending point right here, and then we want to find that area of the region between the curve and either the x-axis, or in some other case with the y-axis, that we have a defined bounded region. Okay, and so one thing I have already mentioned a lot of times enough throughout the lecture here, that the stripe, any stripe that we put inside the region, and those stripes like there, once we're rotating them, it will become the disk. So any stripe that we put inside the region must be perpendicular with the rotation axis. So if we're rotating around the y-axis, in this case right here, placing our eyes looking down, right, then the stripe has to be, yes, the stripe always goes through, the stripe is inside the region, goes through the region, okay, stop at the one boundary and hits to the rotation axis, but the stripe must always be perpendicular with the rotation axis. So just like that, the same here, the stripe going through the region stops at the outer boundary of the region, or stop at one of the boundary of the region and perpendicular to the rotation axis. So here in this case, if our picture here is telling us that we're rotating around the x-axis, and we're placing our eyes here, if we're placing our eyes here, then any stripe inside of this region has to be perpendicular with the rotation axis, so that when we are rotating it, we'll be creating a disk right in front of our eyes like that. Okay, so this is not anything new. I've been saying this throughout the entire lecture so far. Okay, but now another key point right out of that, it's just all along with the rotation axis and the stripe right here. Okay, and I would like to point out a couple other key generalities or key points that I was not able to mention earlier throughout the lecture. So, I mean, if we're looking at either a picture like this or a picture like that, then in the way to make it consistent with the disk methods, then there will be always one thing as following that we can recognize. You see, there must always be at least in a region like this, there's boundary, there's boundary, there's a boundary, the curve is its boundary, and one of the axes here is also the boundary. So for the disk method, then there's always one boundary being a straight boundary, straight edge boundary, where the rotation axis align exactly on that straight boundary. Okay, I'm only saying there has to be one. I'm not saying all of the boundary have to be. I'm not saying that all boundary have to be straight, but there has to be one boundary being straight and the rotation axis. See, so here, it might have fancy boundary, but then there has to be one that's being straight edge boundary, and then the rotation axis aligns with that. Will be aligned with that straight boundary, so that when you do your rotation, then the stripe going through will be perfectly perpendicular with that straight edge boundary. And that's another key point that I want you to put into your understanding. So how about on the other board right here? Let me summarize out those key points. So the first key point I mentioned earlier was that any stripe, okay, any stripe through the region must be perpendicular. So allow me to use that symbol for perpendicular. Must be perpendicular to the rotation axis. So it could be the x-axis or it could be the y-axis, but generally we regard to that as the rotation axis. So any stripe, because these stripes, when we are rotating it, they become a disk in front of us. Okay, so any stripe inside the region or through that we draw, that's drawn through the region, must be perpendicular to the rotation axis. That's the number one thing. I mentioned that, and I believe I've mentioned that many times prior to this point. And then another characteristic, kind of like a characteristic of the region that's good for us to apply the disk method here, is that there must be there must be a straight edge. Okay, I call that straight edge. Okay, let me correct my writing here a little bit. Straight. All right, there must be a straight edge boundary of the region, okay, where the rotation axis is aligned with. And when I'm saying aligned with, allow me to describe that with the graphical interpretation earlier, aligned with, and I really mean the axis, the rotation axis comes together, stays right on that straight edge boundary. That's what it means by the rotation axis is aligned with. Okay, and that's the key point number two. The generality number two, that for you to make sure to double check or as a checkpoint right there for you to know that the disk method being applied in the problem with a situation like this will be successful. Okay, and then another key point to be mentioned here. Is that you see, so it's all about the stripe right here. Any stripe that we're placing here, yes, we know it has to be. So at this point, the requirement of the stripe is it has to be, well, it's inside the region. It has to be perpendicular with the rotation axis. But now another thing right here that I believe I'm a little bit unique in pointing this out to any of my students here, that the stripe, in order to be the disk method, or in order to know that the disk method will be the successful one that lands you into the correct answer, is that any stripe inside of your region here from the rotation axis out to the boundary right there and stop at the boundary, any stripe here will not cross, okay? Any stripe will not cross any other boundary at all. You see, it comes from the rotation axis and it comes to another boundary right here, but it doesn't cross right here. It doesn't cross here. It only starts here and it stops there, okay? So that's another key generality I would like to point out for any of my students. Any stripe, okay? Any stripe does not, okay? Any stripe in a region does not cross any boundary. That's another key point to keep in mind right there. Okay, anytime that you are about to use the disk method right there, because the idea now is that a lot of times, and you can see that throughout all of, the two examples I've delivered so far, and then after this video you will be exploring some other additional examples where I prepare for any one of you to learn right here. Then usually the problem will not necessarily have to indicate clearly for you that, hey, use the disk method, but if you stay focused on these key ingredients or these key characteristics or these key generalities, then you will it will help you to decide which method among, right now I'm only teaching the disk method, but in the later videos, lessons right there, you will be also exposed to other methods. Then these key points right here will help you to decide which method among the many that you have learned will be the best one for you, that will be the most suitable one for you to get the problem solved. Okay, and so here, if you decide to use the disk method, then one thing to keep in mind, or any time that you realize that any stripe that you draw, any stripe drawn through the region, right, and going from one boundary to hit the center of rotation or the axis of rotation, and as long as that stripe does not cross any boundary, then you know that the disk method will work. Or the other way around, if you know that you plan to use the disk method, then it better be that any stripe in the region must not cross the boundary. It doesn't matter where you put the stripe. You can put the stripe here. See, it's only go from one boundary and stop at the other boundary, but it does not cross through any boundary. There's even other cases where your boundary might be kind of like this. Okay, so and there's a straight edge boundary of the region that if we're rotating this around the x-axis, okay, let's see if this method will help. Yes, this method will be excellent for this. All due to the fact that because see, any stripe that we draw right here, any stripe drawn through the region perpendicular to the rotation axis, okay, it's any stripe here, any of the stripe here does not cross the boundary. Okay, does not cross any boundary, because there are cases later on. Allow me to get on the other board, erase some information. Because as problems will later on become more advanced, there will be times where you are looking at a region. See, you got a region. Okay, and then we take that region to rotate around an axis. Let's say we want to choose to rotate around the x-axis here in this case. And so if we're rotating that way, we can always create the stripe. Okay, we can always create the stripe through the region and hit to the rotation axis. See, rotation axis is here. But look at our stripe this time. Look at our stripe this time. The stripe this time from a boundary, from the boundary to the rotation axis right here. That stripe through the region and trying to reach the rotation axis, it does cross in the way how the picture is. The stripe does cross the boundary of the region at some other point right there. And so in this way, you have to now start knowing, in this way, you have to now keep in the back of your mind, once rotated, it's not going to give us disk. Okay, see, it's not a disk shape right there, versus the version we are learning here. Right here, any stripe, see, no crossing through the boundary, through any of the boundary. And so when you're rotating that, it will give you a solid disk. Whereas here, the stripe, initially the stripe, to reach to that center of rotation, the stripe has to cross through. See, it started out from the boundary, but it's crossed through the other boundary right there, one other boundary, or it could be one smooth loop around curve right there. So it crossed through the boundary to hit to that rotation axis. So situation like that, when we're rotating, we're not getting disk. Okay, we're still going to get some kind of cross section, but allow me to explain about this situation in a separate video lesson, in a separate lecture right there. Okay, so in that way, back to that feature number 3 that I pointed out. And that's the most feature that I want to emphasize. It's any stripe must not cross any boundary. Okay, all right. And so the plan now is that at the end of this video lesson, at the end of this video lecture right here, I only deliver 2 examples directly in this particular lecture itself right here. But then outside of this video lecture, I will design as separate, discrete other video lessons right there where I will keep introducing more problems for this method right here. And those examples there are not necessarily organized into, not necessarily ordered into example 1, example 2, or example 3, or so on and so on like that. So the more you view those video lessons of mine about the separate examples right there, the better experience you build in your own confidence about the DISC method. And any of those examples, I will always refer to all detailed explanation I gave in this particular general discussion lecture. Okay?